Now please welcome to the stage, Jacques Ruer.
So good afternoon, everybody. It's nice to make the last presentation of this conference and to see that you are still here. It shows the interest you have in this subject. My speech will be a presentation of the study made on behalf of this Clean Alchemy European project. Clean Alchemy. Alchemy, it means hydrogen metal energy, because the European Union asked us to avoid LENR, cold fusion, such things, but don't worry, it's all about the same thing. I am a lazy boy, so all the slides have been left with HME instead of LENR. I just changed the title, from LENR into HME, because if you compare with the program. So my presentation will have two parts. First, what is an HME heat source? And second, what are the present usage of heat in the industry and how these HME heat sources could be used. So, part one, what is an HME heat source and what are the different types of heat sources, So for the purpose of this study, this HME reactor is a black box. You see a black box, this is the reactor. So we don't look at what it is inside, but in this reference scenario, it generates only heat. And the reactor requires some form of excitation. You see a blue arrow entering this black box called excitation. And the excitation is processed by an excitation supply that consumes some electricity. The heat can go into a heat converter to produce more electricity, hopefully, at the end. And of course, it should go, yes, a feedback is possible. We make a distinction between four types, basically, of heat sources. I'm not going to go into deep details because of a lack of time. For example, I'm not going to detail how we control these different types of reactors, but this is one reason why we have to make a distinction between these types. Type 1, you have to heat the reactor. Type 2, you don't have to heat it, Type 3, this is a self-sustained system, and Type 4 will be discussed in further ICCF conferences, not tonight. Type 1, heating plus excitation. The electricity is used to reheat the thing and also to supply the high exergy excitation. What is exergy excitation? This is any type of energy input, but it is not heat. It may be electrical discharges, it may be hydrogen diffusion, it may be laser impulses, any ultrasounds, anything you imagine except heat. And you see here a sketch with a simplified energy flow. So it's an opportunity to introduce these some parameters. The excess heat, it's easy. This is the heat output minus the energy put in. The coefficient of performance, you know it. This is the heat output divided by the electricity supplied to the excitation unit. And we also introduce the amplification factor. This is the heat surplus on top of the heat you provide. You have more heat out, divided by the electricity required to supply this high exergy excitation. And to give you an example, if we visited this Brillouin demonstration in this conference, this is a type 1 unit, and they claim to have a COP of 1.2, 1.4, but they have an amplification factor of 2, 2.7, maybe 3. These are different things. You have to heat up, especially if the reactor is small, you have high heat losses, but if you have larger reactors and if you increase the insulation, you may very well avoid reheating. In contrary, you will have now to cool it. And this is now type 2 reactor. And if I come back, you see that in fact the excess heat is not changed in terms of watt per kilogram, for example. When you improve the insulation, the amplification factor is also not changed, but the COP is changed. So this is an indication that when you want to evaluate the performance of this kind of LENR reactor, to please you, the COP is not indeed a relevant metrics. You should stick to the amplification factor and also to the excess heat specific energy in watt per kilogram, you know. Now, if it's type 2 reactors, you don't have to heat up, we have to cool it, and the heat can be exported, you know, for usages. You can even recover the heat losses if you do it well. The reactor can be coupled with a thermodynamic energy converter to produce electricity. In this case, you know, this is a type 2. Demonstration is easy. This picture is a little bit complicated. But if you draw a control domain around it, you see that you have to still to introduce some electricity to get some heat out. Now, the type 3 is a unit able to export some electricity. Same thing. If you draw a domain around it, you see that you don't have to introduce electricity, except maybe during the startup phase, and out you get electricity and heat. Nice, huh? Condition for self-sustained operation. I am not going to detail this complicated for demonstration to save time. And type 3 involves automatically a thermodynamic converter. And you know that the efficiencies of these converters is governed by the Carnot efficiency, depending on the temperatures, multiplied by the relative efficiency of this specific engine. So these are typical relative efficiencies, you know, of different types of converters. They are not all equal. Of course, we should not forget that one day we will see direct electricity generators escaping this Carnot, you know, theorem, but it is not considered in this scenario. And here we are. This graph shows the minimum COP you need to make an autonomous system depending on the temperature of the heat delivery and also the relative efficiency of your converter. And indeed, if you have, it seems that there is a slide missing, so I don't insist. Let's go. Now, let's consider this heat usage, you know, in the industry. This picture is a tentative representation and simplification of all heat consumers in the world, you know. So this is adapted from different sources, you know, and none of them give you the data you want. So you have to stretch the numbers to get what you need. In this specific case, this is how many units you have. And the horizontal axis, these heat consumers are classified by this heat input in megawatt from 1 kilowatt to 1 gigawatt. This is also a classification by the temperature. And each column represents the number of consumers for residential purposes, commercial, transportation. And on the right, you see the dark gray columns. These are the power stations. In the center of the figure, you see a group of gray columns. These are all the boilers used in the industry, you know, for paper mills, food processing, alumina production, chemical industry, name it. There are all different, but you have many, many boilers used in the industry. This picture uses a logarithmic scale. It helps because even if this picture is not accurate, an error or 2 or even 10 is almost not visible. At this level, this picture is just fit for the purpose and nothing more. The largest one, this is a dark blue at the back. It represents the 1.4 billion automobiles running in the world, while here, these are just 440 nuclear reactors. And as I said, these temperatures here are just for reference as an indication and nothing more. What can you do if you have types 1 and 2 reactors running at giving you heat at 100 degrees C? Well, indeed, you can supply these heating devices for residential, for space heating and water heating. These are small sizes, huge numbers, and provided the cost is right, because you have the competition of other systems, you should never forget you have other solutions when you want to do something. It could very well be a prime market. If you are able to make larger units, in terms of heat consumption and up to 300 degrees, then you can enter the boilers market. So the only trouble is that each boiler has its own specification in terms of temperature and power, so each problem is unique. Now, type 3, if you go up to 300 degrees and you can produce mechanical power, you can now displace everything related to heating and cooling and displace the heat pumps. So you have many, many applications, energize the heat pumps, sorry. You have access to many applications. Of course, if you go up to 300 degrees C, you may think about electrical generators. Not especially very large. They can be from small size to medium size, but once they are connected to the grid, they can supply absolutely everything, replace absolutely many consumers, starting with the power station, indeed. And in this case, we are talking about huge numbers. Concerning transportation, at the back you see these dark blue columns, classified according to a high temperature. Think about the maximum peak temperature in the cylinder of a diesel engine, it's large. So is that accessible? Well, in this scenario, we are studying different scenarios, but in this specific scenario, we consider that the specific energy, more than 1 kilowatt per kilogram, might not be immediately accessible. Well, again, this is just a Foresight study. And I know that we heard about numbers larger than 1 kilowatt per kilogram, but in this scenario, we say that it's difficult to have this for the moment. And indeed, all prospective studies become obsolete sooner or later, At times, this is because the assumptions prove too ambitious and not reachable. Think about, for example, all the prospective studies made around hot fusion. Probably they made assumptions that will be proved difficult to reach, and all these prospective studies for hot fusion may become forgotten one day. In our case, maybe the assumptions we use are too modest, and this study will become obsolete because the result will be better than our assumptions. So I shall be happy on the day your achievements will supersede the assumption used in this study, at least in this scenario. It does not mean that even in this case, transportation is out of reach, because if you can produce a lot of cheap electricity, the electricity can be used to supply electricity for electric vehicle batteries, to manufacture, to produce hydrogen, and even synthetic fuels, you know. So, even if it is not accessible immediately, it is indirectly. This table is a summary of the different types and the different temperature levels. You know, below 100 degrees C, and even if you have not a self-sustained operation, but type 1 or 2 system like Brillouin Energy, for example, you already have access to large number of units in tens of millions, hundreds of millions of units around the world. So there should be a place for us. Huh? If you do this, you will enter into a learning curve towards higher temperatures, larger sizes, you know, in terms of heat power, and you will be able to supply this boilers market, maybe even the process heat market. But of course, the real breakthrough might very well be the advent of power generators, you know, from in the kilowatt to megawatt range. And in this case, we are talking about billions or maybe tens of billions of units to be produced. So in conclusions, I would say that type 1 and 2 may find a large use for space heating and water heating, provided the economics are right, but this is not considered here. The learning curve will give access to larger units and higher temperatures. The development of large units will open the market for industrial boilers. Type 3 electricity generators will find applications at all scales of power. Transportation requires high specific power. It might not be accessible immediately, but indirectly via the synthesis, for example, of fuel. And the benefit in this case will be that you would not have to change the existing engines, nor the distribution infrastructure to supply energy, liquid, for example, to all these transportation mobile equipment. So this is also to be considered. So this is the last slide of this last presentation of the last day, and I would like to say that you should be prepared for the revolution, because some transitions happen at times very fast. On this photograph, you see on the left in New York City, the Fifth Avenue in year 1900, you see mainly only horse carriage vehicles, you know, only one car. 13 years later, in 1313, same city, Fifth Avenue, you have only now cars, many, many cars. There is even a traffic jam. This is New York. And it went very fast. But we are not in New York City 100 years ago. We are today in Silicon Valley. And in Silicon Valley was the place where several modern transitions that reshaped the world took place, you know. And maybe Silicon Valley could very well be the place to trigger the next revolution about energy. Again, this presentation is just about foresight, but I would like to conclude that we should work together to make this foresight a reality. Thank you.
We do have time for one or two questions.
You never know.
Hi, Jacques. Nicolas here. I didn't quite get the constraint of 1 kilowatt per kilo for transportation. And on average, a car consumes less than 15 kilowatts, and you can afford 150 kilo for that, so it's more 100 watt per kilo, the constraint.
Well, depends what kind of mobile equipment you are talking about. You know, yesterday Georges Egeli was talking about electric planes, and in this case you will need high energy densities. You know, this is just a ballpark. Again, this is a scenario. We don't go into such details because it would be useless indeed for the moment. We have to keep such an effort later in due time when we will be close to the realizations. You know, at this time, we are just delineating the landscape.
Hey, thank you, Jacques. That's actually all the time we have for Q&A. We do need to move on, so thank you again for your time.
Thank you.